Welcome to my lecture on stochastic process. So in this lecture we shall cover up the problems relating to the classification of states and finding stationary transition probabilities. We shall cover very common problems which frequently comes in different competitive examinations. So definitely it will help you in solving these problems. So let us start. Now consider an example. Suppose the transition probability matrix of a Markov chain is given by P equal to 0, half, 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 0, half, then half, half, 0. Now given probability x0 equal to I, this is equal to 1 by 3 for I equal to 1, 2, 3. This is called as the initial distribution of x0, so that the Markov chain has stationary transition probabilities the state space S equal to 1, 2, 3 and classify the states of the Markov chain. So here the initial distribution is given along with the transition probability matrix. The state space is 1, 2, 3. We have to find the stationary transition probabilities as well as we have to classify the states of the Markov chain. Now let us start from the classification. Now before going to the classification, we first draw the transition graph. Now first we shall draw the transition graph. Now this is state 1, state 2, 1 to 2, the half probability, then 1 to 3, this probability is half, then 2 to 1, this probability is half, 2 to 3, each probability half, 3 to 2, this probability is half, 3 to 1, this probability is half. So all the states are communicable. So here all the states are communicable. So the Markov chain is irreducible. So since this is an irreducible Markov chain, all the states belongs to the same class. We can find the property of any one of the state. So let state 1 and the properties of state 2 and state 3 will be same or similar to state 1. Now for state 1. we have f11 star that is equal to summation over n equal to 0 to infinity f11 n. So f110 that is equal to 0. Transition from state 1 to state 1 in 0 states for the first time. f111 this is also equal to 0. Now f112 that is equal to p122 and then p221. Again p123 and p321. So this will be equal to half into half plus this is also half and half. This is 1 by 2. So f112 this is equal to 1 by 2. Now we shall find f113. f113 that is equal to p 121 p231 p311 plus p131 into p321 and p211. So this will be equal to 1 by 2 into 1 by 2 into 1 by 2 plus this is 1 by 2 into 1 by 2 into 1 by 2. So this is 1 by 8 plus 1 by 8. This is 1 by 4. Now similarly we can find f114 this is also equal to 1 by 8. So now f11 star this is equal to summation n equal to 0 to infinity f11 n that is equal to f110 plus f111 plus f112 plus f113 plus up to so on. So this is equal to 0, 0. So this is 1 by f112. So this is f112. This is 1 by 2 plus 1 by 4 plus 1 by 8 plus up to so on. So 1 by 2 taking common 1 plus 1 by 2 plus 1 by 2 square plus up to so on equal to 1 by 2 1 by 1 minus half. So this is equal to 1. So f11 star is equal to 1. So state 1 is persistent. State 1 is persistent. So all these, since all the states are communicable, all the states are also persistent. So now we have to find the mean recurrence time. Mean recurrence time for state 1 that is equal to mu11 that is equal to summation n equal to 0 to infinity n into f11 n. So this will be equal to 0 into f110 plus 1 into f11 1, 2 into f112 plus up to so on. So this is 0 plus 0 plus 2 into 1 by 2, 3 into 1 by 2 square plus 4 into 1 by 2 cube plus up to so on. So this will be equal to summation n equal to 0 to infinity, n equal to 1 to infinity, n equal to 2 to infinity, n into half to the power n minus 1. We have to find this sum. So now to find this sum, consider one plus r square plus r cube up to so on. This is equal to 1 by 1 minus r. This is mod r less than 1. So differentiating both sides, with respect to r, we get 1 plus 2r plus 3r square plus up to so on. This is equal to minus 1 into 1 minus r to the power minus 2 into d by dr of 1 minus r. So this implies 1 plus 2r plus 3r square plus up to so on. This will be equal to minus 1 by 1 minus r whole square into minus 1. So this will be equal to 1 by 1 minus r whole square. And the left side, this will be 1 plus summation r equal to 2 to infinity, n equal to 2 to infinity, n into r to the power n minus 1. Using r equal to half. Now this implies now using r equal to half, we have 1 plus n equal to 2 to infinity n into half to the power n minus 1. This will be equal to 1 by 1 minus half square. So this will be equal to 1 by 1 by 4. So this will be equal to 4. So this implies n equal to 2 to infinity n into 1 by 2 to the power n minus 1 equal to 4 minus 1, that is equal to 3. So using this result, we can get mu11 equal to 3. So this is finite. So state 1 is non-null. Is non-null. Now to find the period of state 1. Period of state 1 we have P111 that is equal to 0. P112. So 1 to 1 in 2 states. So this is equal to P121 into P211 plus P131 into P311. So if we put all these are half, so half into half plus a half into half, this is greater than 0. Similarly, P113 we can find this is also greater than 0. So the period of state 1 that is equal to D1 that is equal to GCD of N such that P11N greater than 0. So that is equal to GCD of 2, 3 up to so on. This is equal to 1. So state 1 is aperiodic. So the state 1 is aperiodic, persistent and non-null. So it is ergodic. So since all the states are communicable with each other, the Markov chain is irreducible and as we know that in an irreducible Markov chain all the states belongs to same class. So all the states are also ergodic. Now we have to find the stationary transition probabilities. Stationary transition probabilities. Now consider P minus lambda I equal to 0. So here we find the eigenvalues of P. So that implies P 0 half 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 0 half then half half 0 minus lambda 0 0 0 lambda 0 0 0 lambda. This is equal to 0. So that implies minus lambda 1 by 2 1 by 2 1 by 2 minus lambda 1 by 2 1 by 2 1 by 2 minus lambda. This is equal to 0. Now by solving this, we can get lambda equal to 1. We can, so since it is a cubic third degree polynomial in lambda, so lambda will have 3 values. So lambda equal to 1 and minus half minus half. So 3 values, lambda equal to 1 minus half minus half. So lambda 1 equal to 1, lambda 2 equal to minus half, lambda 3 equal to also minus half, such that lambda 2 mod less than 1 and lambda 3 mod also less than 1. So when lambda equal to 1, when lambda equal to 1, we have to find out the left eigenvector as well as the right eigenvector corresponding to the characteristic to root lambda. So we consider, so here this is finding left and right eigen vectors. So consider p minus lambda I into x equal to 0 and y dash into p minus lambda I, this is equal to 0. So this implies this will be minus 1 half 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 minus 1 half, then half half minus 1 into x1 x2 x3, this will be equal to 0. So this implies x1 x2 x3, this is equal to 1 1 1. Similarly, by solving this and taking y equal to y1 y2 y3, to y equal to y1 y2 y3, so y dash will be a row vector. So we can get by following similar way, we can get y1 y2 y3, this will be equal to also 1 1 1. So we get left eigenvector as well as the right eigenvector corresponding to the root lambda 1. So now the stationary probabilities are given by limit n tends to infinity p to the power n. So that is equal to summation over j Cj inverse lambda j to the power n into aj. So since we are considering the other two roots are negative, we are considering only the positive root. So we are considering the lambda 1 equal to 1 only. So this will be C1 lambda 1 to the power n into A1, where C1 equal to y1 dash x1 and A1 equal to x1 y1 dash. So using the y1 dash and x1, so we can get C1 equal to, so this is 1 1 1 into 1 1 1, so this will be equal to 3, and C2, sorry, A1 will be equal to 1 1 1 and 1 1 1, so this will be equal to 1 1 1 1 1 1, again 1 1 1. So now limit n tends to infinity p to the power n. This is the stationary transition probability. C1 inverse lambda 1 to the power n A1. So C1 equal to 3. So this will be 1 by 3. So this will be 1 to the power n. This is 1 and A1 1 1 1 1 1 1 1 1 1. So this will be equal to 1 by 3 1 by 3 1 by 3 and 1 by 3 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 1 by 3. So all the rows are identical. So here we can find also, if it is given the probability xn equal to 1, that means after n transition it will be in state 1, this probability will be probability xn equal to 1 given x0 equal to 1 plus probability xn equal to 1 given x0 equal to 2, sorry, this into probability x0 equal to 1, this into probability x0 equal to 2 plus probability xn equal to 1 given x0 equal to 3 into probability x0 equal to 3. So this will be equal to 1 by 3 into 1 by 3 from this 1 to 1. So this is 1 by 3. So we are considering 1 by 3, and this probability x0 equal to 1, this is 1 by 3 given. So this plus 1 by 3 into 1 by 3 plus 1 by 3 into 1 by 3. This is equal to 1 by 3. So the Markov chain has stationary transition probabilities. Markov chain has stationary transition probability. So similarly, you can solve yourself another example. Consider a Markov chain with transition probability matrix P equal to 0, 2 by 3, 1 by 3, 1 by 3, 0, 2 by 3, then 2 by 3, 1 by 3, 0. With probability x0 equal to I, this is also 1 by 3, I equal to 1, 2, 3. So state space S equal to 1, 2, 3. We have to find the stationary transition probabilities. So we can proceed in the similar way to find the stationary transition probabilities. So here we get, if we solve this, we get lambda 1 equal to 1 and other two eigenvalues, they are imaginary. So we shall consider only one eigenvalue, that is lambda 1 equal to 1. So limit, and in just like the previous example, we can find it. Now you can solve similar problems where we have to find out the stationary transition probabilities. So in my next video, I shall consider the stability of a Markov system. So in that, we shall consider the limiting behavior of finite irreducible chains first, then we consider the reducible case. Now thank you for enjoying the lecture.